Okay, so we're about to start learning about non-homogeneous differential equations. But before we learn about techniques for solving them, it's very important that we first talk about the general solution to non-homogeneous differential equations. But before we talk about that, let's just briefly talk about homogeneous differential equations. We know that if you have the homogeneous differential equation, let's just say of the general form, a function of x times the nth derivative of y plus f n minus 1 of x times the n minus 1th derivative. And if we go all the way down to f1 of x times the first derivative plus f naught times y, if all of that is equal to 0, then this will be a linear, nth order, homogeneous differential equation. And if all of these function terms are continuous on what we like to say a common interval of x, then there will be n linearly independent solutions. And we can just label them y1 of x, y2 of x, all the way up to, let's say, yn of x. And we know that if we were to take a linear combination of these n linearly independent solutions, so c1 times y1 plus c2 times y2 plus all the way up to cn times yn, where these c's, these are just n different c values that are all just arbitrary constants. But if we were to take this linear combo, we know that the linear combination of solutions is also a solution. In fact, we like to call it the general solution. And I'm going to denote the general solution to the homogeneous differential equation as y sub h. And the way I want you to try and think about this solution in this video is, if we just had just this differential equation right here, and if we were to plug in the value of yh, then all of these derivatives will cancel and we'll be left with it's all equal to 0. Now let's start talking about non-homogeneous differential equations. So same general form, like fn of x times the nth derivative, and I'm just going to go ahead and just say plus f1 of x times the first derivative plus f naught of x times y, if all of this is equal to some function q of x instead of 0. And q of x can be any continuous function. So if q of x and if all these functions are continuous, then we can go ahead and try and find a particular solution that satisfies this differential equation. Essentially, when we plug in the particular equation to just the differential equation, then we get that most of the functions cancel out, but we're left with this one function q of x. And that's how I kind of want you to think about it for this video. If we had just this differential equation here and we plugged in this yh, would get that it equals 0. And if we were to have this differential equation here and we plugged in yp, then it'd be equal to q of x. So this is the particular solution. But what would be the general solution to this non-homogeneous differential equation? Well, we'll find that the general solution, I'm just going to say y, is equal to this particular solution plus the general solution to the homogeneous differential equation. So this yp plus this up here, this linear combination of our n solutions. Now you may be thinking, why are we including that? I mean, we're not working with the differential equation when it equals 0, we are working with it when it equals q. But that's what we're going to talk about in this video. We're going to talk about why this is the case, and then we're going to do an example. So let's just talk about it briefly in like abstract terms. And I'm not just going to rewrite this differential equation, but I'm going to rewrite it in our linear operator form. So L acting on y represents this differential equation right here. It's fairly long to write out, so I'm just going to do it in the shorthand. And we know that if we had one solution, the homogeneous solution, if we were to plug that in here, let's say L acting on YH, then we know that then we'll get 0 as a result. Basically, this up here. And we know that if we had a particular solution, YP, and if we were to plug in the particular solution to just this differential equation part right here, L acting on YP, then we'd be left with Q of X. So let's see what happens when we add these two together. So L acting on YP plus YH. The particular plus the homogeneous solution. Since this is a linear operator, we say that that's the same as L acting on YP plus L acting on YH. And we know that this is just equal to Q of X plus 0, which means that L acting on the particular solution plus the homogeneous solution is just equal to Q of X, which means that YP plus YH, this particular solution plus this homogeneous solution, is also a solution to the non-homogeneous case. And the reason is, we can see that the solution to the homogeneous case, it doesn't contribute anything. We can always add the homogeneous solution because we know it won't actually contribute anything else in this, like, right-hand side. So that may be a bit confusing in, like, abstract terms when we're working with just, like, these abstract L acting on Y. So let's do an example. Let's do the example: the second derivative of y minus 2 times the first derivative minus 3 times y, all of that is equal to negative 3x minus 5. Now, first of all, let's just say that we found a particular solution, yp. Don't ask how we found it, but let's just say that we found that yp is equal to x plus 1. First of all, let's just check to see that this is indeed a particular solution. So let's take the derivatives ahead of time. So first derivative is just 1 plus 0, or just 1. And the second derivative is just derivative of a constant, that's just 0. So if we're to plug these in, we get the second derivative minus 2 times the first derivative minus 3 times our function. All of that should be equal to negative 3x minus 5. And if we were to factor out everything, we get minus 2 minus 3x minus 3, which is the same as equal to minus 3x minus 5. And negative 2 plus negative 3 is negative 5, so we find that these two are equal, and this particular solution does indeed satisfy this differential equation. But in order to find the general solution, we also need to take a look at the homogeneous case. So I'm just going to rewrite it down here, just the homogeneous differential equation. Y double prime minus 2y prime minus 3y is equal to 0. Now we know how to solve like a differential equation like this. We can just plug in y is equal to e to the rx. And if we were to plug that in, we'll get the characteristic equation r squared minus 2r minus 3 is equal to 0, which means that r minus 3 times r plus 1 is equal to 0. So our two roots are r is equal to 3 and r is equal to negative 1, which means our two solutions are e to the 3x and e to the negative x, which means our general solution is just yh is equal to c1 times the first solution plus c2 times the second solution. So here's the general solution to the homogeneous case. Now let's take this homogeneous solution and add it to this particular solution and see if it's still a solution of this. So just rewrite everything down here. Just mix up the colors a bit. So y double prime minus 2y prime minus 3y is equal to negative 3x minus 5. And this time we're going to test out y is equal to our homogeneous solution, c1 e to the 3x plus c2 e to the negative x plus this particular solution, x plus 1. Now let's go ahead and take the derivatives of these ahead of time. So y prime is equal to 3c1 e to the 3x minus c2 e to the negative x, and then plus 1. And the second derivative, that's just equal to 9c1 e to the 3x, then plus c2 e to the negative x, then plus 0. So let's plug all of these derivative terms back in here and see if this works out. So we get that the second derivative, 9c1 e to the 3x, plus c2 e to the negative x, minus 2 times the first derivative, 3c1 e to the 3x, minus c2 e to the negative x, plus 1. I'm just going to continue down here, minus 3 times y, c1 e to the 3x, plus c2 e to the negative x, plus x, plus 1. All of this should be equal to negative 3x minus 5. So let's start grouping terms and let's start see if we can simplify this. So I'm just going to group all the c1 e to the 3x terms together. So we have 9 minus 2 times 3, which is minus 6, and then minus 3. And then plus c2 e to the negative x times 1, minus 2 times minus 1, which is plus 2, and then minus 3 times 1, so minus 3. And then let's group all the remaining terms together. So we have minus 2 from up here, then minus 3 times x, then minus 3. Now, we can simplify this up a bit. 9 minus 6 minus 3, that's just 0. So we have this exponential times 0. Then we have 1 plus 2 minus 3, that's also 0. So these exponential terms cancel out, and we're left with minus 2 minus 3x minus 3, which is just negative 3x minus 5. So here we're able to see that when we plugged in the homogeneous solution, that it didn't really impact the right-hand side at all, because the homogeneous solution all cancels out, and we get that they're equal to 0. Which means it's just the particular solution that we have here is equal to this, is the reason why we have this right-hand side. So hopefully that should show why the general solution to a non-homogeneous differential equation is both the particular solution plus the general solution to the homogeneous version. And with all that, we're going to start learning how to solve non-homogeneous differential equations in the next video.